All right, let's talk about the third scale when it comes to levels of measurement, and that's the interval scale. So with an interval scale, data can be ordered and differences are meaningful. So on an interval scale, there is a 0 point. Okay, so there is a measurement where you could actually get a zero. Okay, but um, even though you've got a zero, as a possible data value, um, variables can have both negative and positive values, okay, in addition to zero. Zero in this case does not correspond to a complete absence of the measured variable. So, for example, um, if we were to think of um, money in a bank account, so if you think of a bank account, now a bank account, let's say you've got $1,000 in it, it can only go down to $0. All right. This would be an example of what we're going to learn about later, but a ratio scale. All right. The example that I have for an example of an interval scale is measuring temperature in Fahrenheit and Celsius. So when we think of measuring temperature, we're measuring thermal energy. We're measuring heat energy in an object. And, heat energy, when you think of heat in an object, if we think of, a block of iron, okay, a block of iron, like in a hammer or something, um, iron consists of iron atoms that are in a geometric lattice, something like this, and they've got metallic bonds in between them. When a chunk of iron has some heat to it, these atoms are kind of wiggling in place. They're kind of vibrating in place. Now, of course, you're looking at a hammerhead and, the head of a hammer, you can't actually see the atoms moving. Okay. But the hotter the iron gets, the more these kind of wiggle in place. Okay. Um, the same is true for ice, right? Water, right? Water, which is H2O. That's one oxygen atom with two hydrogen atoms attached to it. And in liquid water, these molecules kind of slip around and past each other. But when water freezes, they do hold uh, a lattice structure relative to each other. They kind of hold position. But even though, ice looks solid, these water molecules are kind of vibrating in their spots. Okay, they're not moving around because it's a solid object, but they're still kind of wiggling in their spots. So, when you take water as a solid, at 32 degrees Fahrenheit, the even though it looks like a solid block of ice, the water molecules are still kind of vibrating in their places. They still have some thermal energy in them. So you could get solid ice, solid water ice, colder than 32 degrees. You could get it to be 0 degrees Fahrenheit. In which case that just means you still have solid ice, but now these molecules are vibrating less in their spots. And you could actually keep going and make this colder and colder and colder, and get as high as negative or as low as negative 459.67 degrees Fahrenheit. Now, if you were to get something cold enough in the Fahrenheit scale, or it was negative 459.67 degrees Fahrenheit, Um, what that means is you're at absolute zero. And absolute zero means an absolute uh, complete or an absolute loss of thermal energy. And so those atoms and those molecules in that position are holding still. They are not wiggling at all. They're not moving. That's absolute zero. That's the coldest anything in the universe can ever get is absolute zero. Uh, the Celsius scale is very similar in that you can have 0 degrees Celsius. Remember, that was our definition up above, is you can have zero as a value, but you can also have negative as well as positive numbers. So, if we were going up to positive 100 degrees centigrade, okay, that's the temperature at which water boils. Okay. But if we went at 0 degrees Celsius, okay, that's when water freezes. But even at 0 degrees Celsius, the water molecules are still kind of vibrating. They're kind of vibrating in their relative positions inside the lattice structure of the ice. Okay, but they're pretty much holding position, but wiggling around, and that's what makes it a solid. But you could get it even colder than 0 degrees centigrade, all the way down to negative 273.15 degrees centigrade. So again, you've got negative values and positive values on the centigrade scale. So both Fahrenheit and centigrade are what's called an interval scale. And you can see we've got this ordered, right? From smallest as a negative number to zero, and then above zero where it's a positive number. And we could just keep going. So this is ordered. Um, and the other thing is differences are meaningful, right? Um, we know what it feels like to maybe be at, maybe 98.6 degrees Fahrenheit. That's our body temperature. And when we get a fever and our temperatures go up to 102, we kind of know what that feels like. And if your temperature goes up to 106, we know what that feels like too, right? Um, and the difference between these, you know, uh, it's something you can feel, but it's also something that you could measure. Um, and then likewise, if the temperature goes down, to freezing, okay, you also kind of can feel that difference. The same is true with degrees centigrade. Now, degrees Fahrenheit and centigrade, those are examples of interval scale. And they're examples of interval scale because not only do you have zero in them, but you also have negative values. Oops. You also have negative values in those scales. But degrees Kelvin, if you measure temperature in degrees Kelvin, that's going to be what we call ratio scale. And it too has a zero, but you can't get anything colder than that. 0 degrees Kelvin is equal to absolute zero. At 0 degrees Kelvin, there is zero thermal energy. Okay. Um, so 0 degrees Kelvin is a total absence of heat. An object cannot get colder, so there's no negatives. So this is a different type of scale altogether. All right. So let's go ahead and end this video here. We'll talk about ratio scale next. But I've just given you a heads up of kind of what a ratio scale is relative to an interval scale. Okay, let me know if you have any questions.